All right, our last topic for chapter 6 are geometric sequences and series. So remember we talked about arithmetic sequences, and those were the ones that had a common difference. So basically we're skip counting by number, like 2, 4, 6, 8, 10, or 5, 10, 15, 20. You know, there was a common difference between the numbers in the list. A geometric sequence is another list with a pattern, but instead of a difference, something that you're adding on each time, you have a common ratio called R. And this common ratio is basically what is being multiplied each time. So you're figuring out, this is a list from 1 through 5, and these are my outputs. 4 times what gives me 12? Well, that's times 3. Is that true here? Yeah, each time I'm multiplying by 3 to get my new value. So my common ratio here is 3. So the difference being we're talking about multiplication instead of addition. There are 2 ways to write this, right? So you can write a recursive definition, which is saying, okay, the first a sub 1, the 4, is the value of the first term, and then to find every other term, you take the term before it and multiply it by r. And then you can write that down in one nice equation called the explicit definition, which is saying if you're trying to find any term in the sequence, you can take the first term and multiply it by the common ratio of the term before it. So here's what I mean. Let's do this for the example above. So our recursive definition would be a sub n equals what? Well, it would equal 4 when n is 1 for the first term, right? And then any term above it, you would take 3 times the common ratio times the term before it, and you would be able to find the value. We can write that more simply in this explicit definition by saying it's equal to a sub 1, which is 4, times the common ratio, which is 3, and take away 1. So let's try that. Like if I was trying to find the third term, I would do 3 to the second power, right? So that would be 6, 9, Ms. Harrington. 3 to the second power would be 9, and 9 times 4 is 36, so that works out. This is basically an equation you can use to find any term in this list. Let's try another one. So given that a sub n equals 5, so 5 is the first term, and then to find any other term, you take 1/2 times a sub n when n is greater than 1. Write the explicit definition. So what are some things I know? I know that a sub 1 is 5, and I know that the common ratio is 1/2. So my explicit definition, remember, is this. So I can write it as a sub n equals a sub 1, 5, times my common ratio, which is 1/2 to the n minus 1. In this one, they're giving us a list. 12, 9.6, 7.68, 6.144. Is it a geometric sequence? If so, write the recursive definition. Okay, so how am I going to check if there's a common factor being multiplied here? Well, I can use division, right? So I can take the second term and divide it by the first term. What do I get? 9.6 divided by 12. Uh, 0.8. Let's try it again. Let's see if it's consistent. 7.68 divided by 9.6. Also 0.8. Okay, that's looking like that's our common ratio, but for good measure, let's just try one more. 6.144 divided by 7.68, and yep, I get 0.8. So my common ratio is 0.8. My a sub 1 is 12, so they want the recursive definition, so they want this one. A sub n equals 12 when n is 1, and then it's equal to 0.8 times the term before it when n is greater than 1. If you wanted to write the explicit definition, you could. It would be a sub n equals, a sub 1 is 12, times common ratio 0.8 to the n minus 1. And our answer is yes. It is a geometric sequence. Now, always don't forget to go back and see if you're actually answering the question. All right, so we hit the first part, what's a geometric sequence? And now there's another part to this, a geometric series. So that series is just representing the sum of a certain number of terms. So if it said find the geometric series of the first 5 terms, you would just be adding those first 5 terms together. And so this big symbol right here is the summation symbol. This is saying the way you would write mathematically geometric series is the sum from this first term they tell you to the nth term, and you would be summing up the explicit definition or the explicit formula, right? Because each time you're going to get a different value depending on which term you're on, and you're going to add all those up. And then you can do this by simply using this formula. This has been simplified to come out to this. If you would like to see the proof of why the summation of all the terms can be found by using this, you can look on page 243. And we're going to use this to answer some of these questions. So the first one says find the sum of this. So it's a geometric series. They want us to sum up the first 7 terms, right, from 1 to 7. So I know that. So n, the number of terms I'm summing up, is 7. What is this? 3 is right here, a sub 1, and this in the parentheses is my r. So a sub 1 is 3, and I know my common ratio is 2/3. So now I have all these variables, I can just plug it in here. I don't need to make a list of 7 terms and add them up. I can just use this. So a sub 1 is 3 times 1 minus, our common ratio is 2/3 to the n, and our n here is 7, all over 1 minus 2/3. When I worked that on my calculator, I ended up with 2059 over 243. Well, that's not right. I'm going to actually work this out. Let's see what we get. I skipped some steps. So let's see what we get when we do this. 2/3 to the 7th. Whoops. Do that first, to the 7th power. Okay, 1 minus, I actually should have done it here, 2/3 to the 7th. Times 3. So this comes to 2.82. I'll round it to 3, 4 over 1 minus 2/3 is 1/3, right? So then I could say this whole thing is being divided by 1/3, which comes out to be 8.473. The answer in your textbook has a fraction, but the value should be the same. Yeah, so they have 2059 over 243, which is the same value, 8.473. So if I took the first 7 terms of this geometric sequence and added them, it would be around 8.473. Okay, now let's go backwards. They're giving me this geometric sequence. Well, they're telling me it's a series, which means they're adding it up. And they're saying how many terms are here. So we know it's at least 1, 2, 3, 4, and then there's some in between. So to figure out how many terms there are, we're trying to solve for this n, right? So let's see what we have. Well, first I can figure out the common ratio. What's the multiplication factor each time? And you could do that, right? You could sit here and divide 300 divided by 200, 450 divided by 300, and I can see my common ratio is 1.5. I know a sub 1 is 200. So the only thing I don't know is n. That's the thing I'm trying to find. So let's set this up. We can use, let's use this formula to see if we can find n. Because we can use any term, right? Let's use, so we know this is the nth term. So we know that that is the value of a sub n. This is a sub n. So I could come over here and also write a sub n is 7,688.7. So now I can plug that in here. 7,688.7 equals a sub 1 is 200 times 1.5 to the n minus 1. Now I'm just solving this for n. So the first thing I can do is divide each side by 200. So that leaves me with 38.445 equals 1.5 to the n minus 1. And now here we are with our variable we're solving for in an exponent. So what can I do to get it out of the exponent? Let's try taking the log of each side. So the log of 38.445 is, I just had my good pencil and I sharpened it, now I don't know where to put it. Story of my life. Okay, equals the log of 1.5 to the n minus 1. Now I know I can take that to the front. Log of 38.445 equals n minus 1 times the log of 1.5. So the log of 38.445 divided by the log of 1.5 equals n minus 1. And so really all I have to do to solve for n is move that 1 over. So I'm just going to erase this. It's going to be plus 1 equals n when I move that 1 over. So I'm running out of space. So now when we go ahead and solve for that, log of 38.445 divided by the log of 1.5 plus 1. So n is 10. So it's close to 10, right? Because we have a bunch of rounding. So there are 10 terms in this series. 10. So that's how you can use these things to go back and forth to find the number of terms or to find the sum. All right, that's it for chapter 6. See you next time.